Right. Next topic is Fourier series. Now, Fourier series is a series expansion of given functions. We can expand a function into an infinite series in the form of infinite series given by this formula. A naught by 2 plus n1 to infinity is the summation an cos n pi over px plus bn sin n pi over px. Minus p to p is the interval which is given to us. F is a function which is also given to us, where a naught, an and bn, these are three coefficients of the Fourier series. We have to solve these integrals to find a naught, an and bn. We put the function here in this integral, integrate from minus p to p with 1 over p outside, and so on over here, and we find a naught, an and bn, put the values over here, and that gives us the Fourier series. I hope that you already know series expansion, because there is in calculus we do Taylor series and Maclaurin series. Okay? The difference between Taylor's and Maclaurin's and Fourier's is these two require the function to be continuous, whereas a Fourier can be expanded for a function which is not continuous. Okay? For example, let's start with a very simple example. F of x equals, our first example is 0 when x is between minus pi and 0, and it is 1 when x is between 0 and pi. Right. As we can clearly see that the function is not continuous at 0, but still we can expand the Fourier series for the function. The first observation is that p equals pi, because our interval is between minus pi to our interval is minus pi to pi. Right. So let's start the integrations. First we need to do a naught. A naught is 1 over p integral minus p to p f of x dx. That will give 1 over pi minus pi to pi f of x dx. Because our integral is, our function is defined in two definitions. Minus pi to 0 is a separate definition, which is 0. So minus pi to 0 is 0, and then we don't need to write this part because it's going to be 0 anyway, but just the first time, because we are learning the concept, so I'll write it to complete the reason. So clearly the first integral, this one goes to 0, so no need to write it any further. The second integral, that gives us integral of 1, which is x, so 1 over pi is outside, 0 to pi. So 1 over pi times pi, our answer is 1. So that is our first integral. Right, the second integral is an. An is again 1 over p minus p to p f of x cos n pi over px dx. Okay? So that becomes 1 over pi minus pi to pi f of x cos of pi, p is equal to pi, okay, because our interval is minus pi to pi, so p is equal to pi. That will cancel out this pi, and we will get cos nx dx. Now again, minus pi to pi minus pi to pi, so minus pi to 0 part will go to 0, just like our previous integral. Only the 0 to pi part, we have function equals 1, so we will write the integral only from 0 to pi, so it becomes 1 over pi 0 to pi, and the function between 0 to pi is 1, okay? F of x is 1, so we only get cos nx dx. And that is a very simple integral to solve. 1 over pi cos nx gives sin nx over n, 0 to pi, and that would be 1 over n pi. We can multiply n and pi together, and then first pi substituted in, and then 0 Right. Sine n pi is 0. Okay, you can this is a general rule. You can check with your calculator as well. Sine n pi for all integers values, okay, for all integer values is 0. You can check with your calculator sine pi, sine 2 pi, sine 3 pi, all these values are 0. So sine n pi is 0 and sine 0 is 0, we already know that. So that's using these two results, we can say that an equals 0. Right, now we come to bn. Bn is 1 over p minus p to p f of x again, sine n pi over px dx. Remember that this pi is not because our interval is pi. Okay, no, this pi is in the formula. Okay, this pi is in the formula, so it will be pi for all the questions. Okay, you see this pi, even if interval is, let's say, -2 to 2, we still have this pi in the series. Okay, that's part of the formula. Right, so this becomes, I'll write this time directly, 0 to pi, 0 to pi, and f of x is 1 there, so sine of nx dx, because minus pi to 0 will go to 0, just like here, minus pi to 0 will go 0, and 0 to pi, our function is 1, so we get 0 to pi, function is 1, and that's left. 1 over pi, in this case, the integral of sine is minus cosine over n, and 0 to pi, that will become minus 1 over n pi cos n pi minus cos 0. Alright, let's see one more result, that is minus 1 over n pi minus 1 power n minus 1. Why cos of n pi is equal to minus 1 power n? Why is that true? We will see. It's very easy to see. Cos pi is minus 1. Okay? Cos 2 pi is plus 1. Cos 3 pi is again minus 1. Cos 4 pi is again plus 1. As you can see very clearly from here now, that cos n pi is minus 1 power n. So when n is 1, the answer is minus 1. When n is 2, the answer is plus 1. If n is 3, again minus 1, and so on. So that is another result which we can remember. We can bring this minus inside if we would like to, otherwise we can leave the answer here where it is, or we can do one more step, and this becomes plus and this becomes minus over n pi. Right, so now we have a naught, which is 1, we have an, which is 0 over here, and we have bn, which is over here. Now we put the values, 3 values here in this formula, and we can write that f of x equals a naught by 2 plus summation n from 1 to infinity minus 1 power n minus 1 over n pi into sine of nx. How did I get sine of nx? Because p is pi, so this cancels again, and we get sine of nx, and an is 0, so we don't have this term. So that is our Fourier series for the given function. Okay, let's do one more question of the same style. Our next question is find Fourier series for f of x equals 0 between minus 1 and 0, x between can see that p is 1 because our interval is -1 to 1. Okay. Our interval is -1 to 1, so p is 1. Right? Same story again. A naught equals 1 over p minus p to p f of x dx. Again, our function has two definitions, but one of them is 0, so no need to write that one as we did in the last example. Second one, 0 to 1, the definition is not 1. The definition is x. Again, just like the last question, minus p to p. So we must divide the integral into two, -1 to 0 and 0 to 1, but because -1 to 0 is 0, so no need to write, just like we saw in the previous example here. So -1 to 0 is 0, so we don't need to write that part. This one gives x squared by 2, 0 to 1, and that gives 1 by 2 minus 0, so in other words 1 by 2. Right, an is 1 over p minus p to p f of x cos n pi over px. Okay, that gives, once again, the one outside is 0, this one is 1, so no need to write. -1 to 1, we have -1 to 0, which is 0, and 0 to 1 is x, so that becomes cos n pi x dx. This integral is by parts, and this time it is easy to calculate. We can just make this table, the famous table which we use. So we take derivative of the first one, okay, d by dx of the first one, and integral of the second one. Integral of cos n pi is sine 1 over n pi sine n pi, and integral of sine n pi is cos n pi x. So we keep this plus and minus and multiply and multiply, and this gives 1 over n pi x sine n pi x between 0 and 1, minus, and this minus will make plus, and that would be 1 over n square pi square cos n pi x, again 0 to 1. That gives 1 over n pi. When we put 1, this becomes sine n pi minus sine 0, and here when we put 1, we get cos n pi minus cos 0. And we know already from previous example that sine n pi is 0, sine 0 is 0. So it means our answer is 1 over n square pi square minus 1 power n minus 1. That is our en. Similarly, Vn is 1 over pi minus pi, 1 over p minus p to p f of x sine n pi x dx. Again, p is 1, so no need to write here. And once again 0 to 1 x sine n pi x dx. Because -1 to 0, the first part is 0. And once again we repeat our exercise with by parts. Sine n pi x, take derivative of this and take integral of this. Derivative of x is 1 and 0, integral is -1 over n pi and -1 over n square pi square sine n pi x, and plus and minus and multiply. That would give -1 over n pi minus 1 over n pi x cos n pi x 0 to 1 plus 1 over n square pi square sine n pi x 0 to 1. That is -1 over n pi When we put 1, we get cos n pi minus cos 0. Oh, no, not made a mistake. Yes, I also made a mistake here. 0 cos 0. So this one, 0 outside as well. 0 sine 0, but that goes to 0 anyway. Right. So this one, when we put 1, when we put 0, that is 0 times cos 0. So do not forget there is an x outside. Plus 1 over n square pi square sine of n pi minus sine of 0. Okay. Now this term goes to 0 because there is multiplied with 0. This term goes to 0 because sine n pi is 0. This term goes to 0 because sine 0 is 0. So we are left with minus 1 over n pi minus 1 over n, because cos n pi is minus 1 over power n. Now we write our series f of x equals a0 by 2 plus summation n from 1 to infinity a cos n pi x dn sine n pi x. So let's put the values. That becomes 1 by 4 plus 1 to infinity an is over here 1 over n squared minus 1 over n. Alright, so this gives x cos n pi x, multiplying these two, and then minus and minus make plus 1 over n square pi square sine n pi x. Then we put 0 and 1, 1 first, 1 for this x, and this is cos n pi minus 0 times cos 0. Do not forget this x outside, that will get 0, and that is why this term goes to 0. Cos 0 is 1, but 0 multiply 1 is 0. And from here we get sine n pi, that goes to 0, and then minus sine 0, that goes to 0. So these three terms go to 0, and we get cos n pi, which is minus 1 power n. Now we have our a0, which is 1 by 2. a0 is 1 by 2. an is over here, and bn is over here. Now we put the values into the formula. So 1 by 2 divided by 2, that will make 1 by 4, and that's the value for an, and with plus becomes minus because we have an extra minus here, and minus 1 over n pi. And that is our Fourier series for this function. I think I made a mistake somewhere here. Let me correct it. Yeah, here it is. This one is 1 minus 1 power n. That's better now. Alright, now you'll see a quiz. Let us continue Fourier series. The next thing is kind of a little trick we sometimes use in solving integration. It involves two definitions, very simple definitions. First is even functions. We have used the word even and odd for numbers, but now we are going to use it for functions. A function is called even function if we replace f with minus x, x with minus x, and it does not change. Similarly, an odd function is a function if we replace x with minus x, we can take x out. Let's see a couple of examples. For example, if f of x equals x, so we replace x with minus x, and that is minus x, which of course is equal to minus f of x, so it's an odd function. If f of x is x squared, then f of minus x would give minus of x whole square, which is x squared, and hence it is x squared, so x vanishes, it is an even function. Similarly, f of x equals x cubed, f of minus x whole cube, minus can come outside, and we can write minus of f of x. It means it is an odd function. Now you got the idea. Let's see one or two trigonometric functions which are very famous ones. So what about sine x? F of minus x, sine of minus x. We know from trigonometry that when there is a sign minus inside sign, it can come outside. So sine x is an odd function. If we have cosine x and we replace x with minus x, cosine of minus x, again we know from trigonometry that minus inside cosine vanishes. You can use your calculator to check last two. Just put any values for x with minus inside and minus outside, and you will see that these two are equal, and in this case the minus without minus they are equal. Right, now there are functions which are neither even nor odd. So all these functions are either even or odd. For example, e power x, a very famous function, e power x. If we put f of minus x, we get e power minus x. Now we can clearly see that this thing is not equal to minus e power x. Minus cannot come outside. Okay? And also it is not equal to e power x, because minus cannot vanish. So it means the function is neither even nor odd. So that's also possible. So actually there are three types, whether the function will be even or odd or neither even nor odd. The result we the reason why we discuss even and odd, we say if f of x is even, then integral minus a to a f of x dx can be written as 0 2 times 0 to a f of x dx. Well, this one maybe it doesn't seem to be a big benefit, but there are functions which are neither even nor odd. For example, let's say f of x equals e power x. If we replace x with minus x, e power minus x. Now x minus cannot come outside, like minus of e power x. It's not equal to minus of e power x. It cannot come down. Or it cannot vanish either. It's not equal to e power x either. So this function is neither even nor odd. So there are three types. It means either the function is even or odd or neither even nor odd. Why do we study this? If f of x is even, then the integral minus a to a f of x dx is equal to 2 times 0 to a f of x dx. And if f of x is odd, then minus a to a f of x dx equals 0. Note that the very important point is the formulas are only valid, it will only work if integral is from minus a to a. Okay? It will not work from 0 to a. Okay? So if the function is odd and we are integrating from 0 to a, then we don't know. Then we have to integrate and find out whether it's 0 or not. Okay? So let's see a quick application of this thing. Sometimes it's very useful. One more thing. Let's say if f is even and g is a function which is odd. Okay? Just like our so if f and g are multiplied, okay, then even multiply odd will give odd. Okay? And if f multiply f, even multiply even, that will give even. And if g multiply g, that is odd multiply odd, that will also give even. Okay? So two odd functions, or rather, yeah, it's almost clear. So I'll put them here as well. So if an even function multiplies an odd function, we get an odd function. If an even function multiplies an even function, we get an even function. And if an odd function multiplies an odd function, we get an even function. Right. Our question is, find Fourier series for the following function: f of x equals x, and x is between minus 2 and 2. Alright, a naught 1 over 2 minus 2 to 2 x dx. As you can clearly see, p equals 2. Now x is an odd function. Clearly x is odd function. So if x is odd function, minus a to a integral of x should be 0. And our an is minus 2 to 2x cos n pi over px. Again, it is 0. We can say directly, because x is odd, cosine is even, and we know that odd multiply even is odd. So x cosine n pi by 2x is an odd function. We can add the word n here. So this is, we can say this directly. Even in exam we can say this directly, because this is an odd function and integration is from minus a to a, so the answer is 0. This is enough explanation. We don't need to solve the integral completely. Now we come to Bn, and 1 by 2 minus 2 to 2 x sine n pi by 2x dx. Now this is odd. Again, sine is also odd. It means the whole function is even. Okay, we can write 2 times 0 to 2 x sine n pi by 2x dx. Let's see if it can be of any benefit to us. X sine n pi by 2x. We differentiate this one 2 times, integrate this one, minus 2 over n pi cosine n pi by 2x, and then again minus 4 over n squared pi squared sine n pi by 2x, and plus and minus So this is equal to, I'll write two terms separately, minus 2 over n pi, this is n pi x cos 0 to 2, and the second one is plus 4 over n square pi square over n square pi square sine of n pi by 2x 0. I'll write the answer directly. I hope you can get the rest of the steps very easily. The final answer is this part goes to 0, this part, because sine of n pi goes to 0, sine of 0 goes to 0. From this part we will get one term, because this x goes to 0 will go 0, and we will get minus 4 over n pi cos of n pi, which we can write as minus 1 power n if we would like to. And our Fourier series for the function a naught is 0 and summation n from 1 to infinity, we can write 4 over n pi minus 1 power n plus 1 into cos n pi by 2x. Here I have used minus into minus 1 power n, can be written as minus 1 into this, which means minus 1 power 1 minus 1 power n, and can be written as minus 1 power n plus 1. Okay, so that's what I've used here. This minus goes into the power of minus 1 power n and makes it minus 1 power n plus 1. And that completes our question. One last thing in the Fourier series is half range series. Half range, so far we are calculating a Fourier series over minus p to p. Okay? All the questions we have done are from minus p to p. What if we are given 0 to L or 0 to something? How will the formula work? Actually, all these formulas, all the formulas in our Fourier series questions, they only work if our question is our function is defined from minus p to p. It is very important for the series to be defined from minus p to p. Now, what if it is not defined from minus p to p? What do we do then? For example, we have a question, f of x equals x square, and x is defined from 0 to L. L is any number, so let's say 0 to L. Now our formulas technically will not work. Okay, what we do in this situation is we can if we look at the graph of the function, so 0 to L, it's a parabola, very simple graph. Let me try a better. So 0 to L, this is the original function, 0 to L x square. There are two possible extensions. First extension is we extend the function this way. First extension is we extend the function this way. Minus L to L, or we can extend the function like this. Okay, so there are two possible extensions of the function. This one is as an even function, and this one as an odd function. Okay? So generally the question on this type of functions is asked like this: find a Fourier cosine series and B Fourier sine series. Both are possible. For this function, both are possible. Okay. So let's see how it works. So the solution, I'll write the formulas within the question. For Fourier cosine series, our formulas are A naught equals 2 by L, 0 to L, f of x dx. Okay? So that's the formula. So that becomes 2 by L, 0 to L, well, because L is L this time, so no need to worry about anything, x square dx, which is equal to 2 by L x cubed by 3, 0 to L, so 2 by L, L squared by 3, or in other words 2 by 3 L. L cubed, so L squared. Right, similarly an would be 2 by L, 0 to L, f of x cos n pi over Lx, which will become 2 by L, 0 to L, x square cos n pi over Lx dx. You can see that you have to do by parts, and it will have three steps: x square cos n pi over Lx. So x square becomes 2x, then it becomes 2, then it goes to 0. And cos n pi over Lx, when we integrate, it becomes L over n pi sine n pi over Lx, and then it becomes minus L square over n square pi cos n pi over Lx. Put this little bit down. And then from minus L cube n cube pi cube sine n pi over Lx, and then we multiply this way, plus minus plus, and then we put the limits. So this will give 2 by L into L over n pi x square sine n pi by Lx, 0 to L, plus 2 by L again, this one, 2 by L again, and plus from here, multiply 2 L square, this is L square, this is L, n square pi square, so this 2 and this L square, 2L square over n square pi square, cos n pi by Lx, 0 to L, and the last one is minus 2 by L again, this 2 by L. I don't want to put a big bracket for 2 by L, so I'll multiply it with every single number inside. So this 2 and this 2, that will make 2L cube over n cube pi cube sine n pi over Lx, 0 to L. You can see in the details that when you put L here, that makes sine n pi, that goes to 0. When you put 0 here, sine goes to 0. So this whole term goes to 0. Same is the case with this one. Same is the case with this one. So we get the answer is from here, okay? From the second term. There should be an x here. I have missed x. This one, this x. That x is missing. So again, when we put L, we get some term, and when we put 0, this x will make it 0. So the only thing, something is going wrong here. So an finally will be, I'll write the direct answer, 4 L square minus 1 power n over n square pi square. Okay, 4 L square. I think 4L, not 4L, 4L, because this 4L square. Now let's write the Fourier series. So Fourier cosine series. Note that in Fourier cosine series we do not calculate Bn because we have extended the function. This one is for Fourier cosine. This one is for Fourier cosine. Okay, even extension. And Fourier sine, and for Fourier sine this is odd extension. When the function has become even, Bn will become 0. So no need to write Bn for Fourier cosine. And our f of x equals a naught by 2 plus summation n1 to infinity an cos n pi over lx. And we put the values of a naught. A naught is also 2 by 3 l square. Make a little more space. Let's start here. 2 by 3 l square. When this 1 by 2 multiplies, so we'll get 1 by 3 l square plus summation n1 to infinity. An is 4 l square minus 1 power n over n square pi square into cos n pi over lx. So that is our Fourier cosine series. For Fourier sine series, we will only calculate Bn, which is 1 by L, which is 2 by L, 0 to L, f of x sine n pi by lx dx. For Fourier sine series, a naught and an are 0. Okay? So this time it will be 2 by L integral 0 to L x square sine n pi by lx dx. I'll write the answer this time directly. It's almost exactly the same as we have done the previous one. So I hope you can solve it yourself. 2l square, this is l square, minus 1 power n plus 1 over n pi plus 4l square over n cube pi cube minus 1 power n minus 1. And in this case, the Fourier cosine series is only summation n from 1 to infinity bn sine n pi over lx, and we just put this bn over here, we put this bn over here, and that gives the series. That's all.